In our final video for Unit 2, we're going to talk about what are called alloys. So we know a lot of times when you combine two nonmetals together and they form a bond, you create a covalent bond. Okay, when you take a metal and a nonmetal, put them together, it makes an ionic bond. Okay, but what if you take two metals, and let's say they're melted, they're in a liquid form, and you pour them together, and you've got a mixture of these metals now. Okay, do they form a bond? No, they do not. Okay, if you take iron and chromium and melt them both and pour them together, yes, they will mix together, but no, they will not form any type of bond. They will form what's called an alloy. Okay, and it doesn't necessarily have to be two metals. It can be multiple metals, and you can even have some non-metals mixed in there as well. Okay, so an alloy is a mixture. It's a homogeneous mixture. You might call it even a solution, where you've melted multiple metals together and poured them together and mixed them together. Okay, really that's what steel is. Steel is a mixture of iron and chromium and different metals, and sometimes they use carbon in them, and they use different things to make the metal lighter, make the metal stronger, to make steel the best metal it can be. So an alloy, again, is just a mixture of different metals that sometimes include some nonmetals. Okay, now within alloys, there are two different types of alloys. One is called an interstitial. Okay, and remember, just like intermolecular forces, inter means between. So that's how I remember the difference between them. Interstitial is like intermolecular, and that it's between two or more atoms. Now, how does that help us remember what it is? Basically, in an interstitial alloy, you've got the pieces, or you've got the, let's say these are the iron. Okay, so these are all atoms of iron. And then what you have to use to make an interstitial alloy is you have to use smaller atoms that basically fit in between these spaces right here. And a lot of times what they use is they use carbon for this. And by adding that smaller atom in between the spaces between the metal atoms, what that does is it makes that steel, or in this case the metal, stronger. Okay, so you've got smaller atoms that fill in the spaces between, and really remember this is like 3 dimensions. So there's iron atoms that are out here, and there's iron atoms on the other side. And they fill the space between the iron atoms in this case, in the case of steel. Okay, when you have an interstitial alloy, they are less malleable, which means you can't shape them as well. They're also less ductile, which means in terms of making wires out of them, you can't do it as well, because that presence of these smaller atoms makes it more rigid and less flexible. But think about like a beam in a building supporting a floor. You don't really need it to be malleable and ductile. You just need it to be nice and strong and rigid, so that it doesn't bend. You don't want it to do those things. Okay? So that's an interstitial alloy, is the small atoms filling in the spaces in between the metal atoms. Okay? Here's an example of this. So here, the larger atoms would be nickel. The smaller atoms would be boron. And again, to be interstitial, it has to be smaller. So if you have like an alloy of sodium and potassium, well, sodium and potassium are pretty close to each other. Potassium does have one more electron shell, but usually when you have an interstitial alloy, you have one of those smaller elements up towards in that second shell. Boron, carbon, nitrogen, or even oxygen can be used. Okay, if you have an alloy of sodium and potassium, that's probably not going to be an interstitial alloy. Okay, so here's all the borons here, and then the nickel is the larger clear sphere there. The other type of alloy that we should be familiar with are what are called substitutional alloys. And in a substitutional alloy, you're taking one of the metal atoms away and you're replacing it with a different atom that is similar in size. So like in terms of sodium and potassium, that's more likely what you would see in that case, in terms of what type of alloy that would be. So one metal's atoms are replaced by another metal's atoms. That's, again, roughly, they're of a similar radius. Okay, for example, when you make brass is a mixture of copper and zinc, sometimes a little different, but in general, basically some of those copper atoms are replaced with zinc atoms, and the two of those together produce a different color. Okay. And again, looking at the periodic table, copper and zinc are right next to each other. Okay, copper and zinc would never form an interstitial alloy because in terms of size, they're both very, very similar in size. So copper and zinc absolutely would form a type of substitutional alloy. Okay, similar to interstitial though, they do have reduced malleability and ductility, and their densities typically lay between the density of the component metal. So the density of a copper zinc substitutional alloy would be somewhat similar between the density, obviously, of regular copper and regular zinc. Okay, here's an example of this where you see, for example, steel is very, very common here. Okay, a lot of times with steel, you can purchase what's called stainless steel, and what stainless steel does is it doesn't rust, which is really, really nice. Okay, rust is very brittle. It breaks apart really easily. It makes the metal much, much weaker. Okay, and so what they do is they replace some of the iron atoms, you can see it right here and right here, with chromium atoms. Okay, because chromium oxide is not the brittle, weak compound that iron 3 oxide is. Iron 3 oxide, Fe2O3, is the compound for rust. Okay, but if you replace those iron atoms on the surface of the metal with chromium, then when the chromium forms those oxides, then it doesn't form into rust. It creates chromium oxide, which doesn't have those same properties that rust does. So notice here that the chromium atoms are roughly the same size as the iron atoms, so that makes it a substitutional alloy. And again, they react with the oxygen in the air rather than the iron, and that eliminates rust forming on the surface of the steel. Okay, now this is still, notice the carbon's in here too. This one is a type of substitutional alloy on the surface of the metal, and then you've got interstitial components of the alloy are inside where the carbon is strengthening that steel. All right, and then the last thing we're going to mention here, which is not a big deal here at all, is when we talked about network covalent bonding, and for some reason they put it here with alloys, then this is not an alloy at all. This is just sometimes with covalent compounds. Typically covalent compounds are gases, sometimes they're liquids, okay? But covalent, remember, which is just another word for molecular, sometimes you do have solids in there, and especially when you have those really, really strong bonds, you have what are those network covalent solids, okay? So in comparison to network covalent solids, so remember diamond, silicon dioxide, there's a couple of boron compounds that are network covalent compounds. Okay, molecular solids, which is what we're talking about now, have very, very weak London dispersion forces between them, which produce, again, these low melting points compared to diamond and sand. They have very, very high melting points. And again, they don't conduct electricity at all, just like the network covalent solids do. Okay, and there's not very many of these, because typically when you have those weak London dispersion forces, you're going to have typically things that are gases or liquids. And so most of them are not solids because they're not strong enough to stay together in the solid form. Okay, but iodine, I2, can actually be a solid at room temperature because I2 has a huge electron cloud. You've got, between two iodine atoms, you've got 106 electrons. So that's a really, really big electron cloud that can be, that's very, very polarizable. And so it is a solid at room temperature. Most other molecular solids are, again, liquids, like Br2 is a liquid. But honestly, the large majority of them are gases because, again, those weak London dispersion forces simply don't keep them together in the solid form. And I hate to tell you, folks, but that's the end of Unit 2. I know you're sad about that, aren't you?